Welcome back to our lecture on finite elements. And as for a start, I would wish everyone a happy and especially a healthy new year. And I'm glad that you're still with me on this lecture here. And yeah, what can I say? We're slowly approaching the finalization of our FEM. So what we're going to discuss today is the assembly of the operators, meaning that we are actually putting together all the ingredients that we have discussed so far. And yeah, aside of the diffusion problems that we have discussed already many times throughout the semester, we will see that there is some generalization doable, and it's quite simple to also transfer the concept to include reactive and convective operators. So what's on schedule for today? Firstly, I want to do a bit of an extensive recap because I think it's important to get everything in order that we have done so far. So yeah, if everyone has completed the assignments from the last weeks and also discussed those few points that I've mentioned in the before Christmas, then I think it will be easy to follow my recap. And otherwise, if you have problems with certain points, I would ask you to revisit the lectures on the specific topic. And then after doing this recap, we are talking about the assembly of the actual linear system. So we are putting together the load vector and the stiffness matrix, firstly for Poisson's equation, so the equation that we have discussed the whole semester. And then we will generalize this to more abstract diffusion, reaction, and convection terms. We'll also motivate what they mean and why they are important. Then at the end of section 2, we will address a very important open question. I'm not going to say what the open question is as for now, so you can take the rest of the lecture to also, fantasize about what question is open. And then in the end, of course, you want to see some pictures finally, and we're going to get some results for Poisson's equation, for different types of diffusion, reaction, and convection problems. And we are going to get a short outlook on singularly perturbed problems. So we'll talk about what that means, as to show you the limits of the FEM that we have implemented so far. First order of business today, as I said, a little more extensive recap. So what we want to do is we want to start from a partial differential equation like this. So minus Laplacian of u equals f in the domain omega, and Dirichlet boundary conditions on the boundary of omega, some right hand side f, and we want to solve it for u. And starting from this, we want to arrive at a linear system, some matrix S times a vector U equals L. And this is supposed to give us a solution approximation in the form of a dot vector U, so some vector with values of an approximated solution at certain important points. Because linear systems are something that can actually easily be solved on the computer, so that's where we want to go. Yeah, and then if you have this dot vector, then it's pretty simple. Then you can just visualize the solution, work with it, and yeah, whatever. Okay, the open question is how to get there. And for this, we take the first step and derive the weak formulation. So what have we done? We have multiplied our PDE with the test function, then integrated over the domain omega, used the Gaussian theorem, and then switched to appropriate Sobolev spaces, right? So this gives us the weak form of the problem. Find u in h10 such that the integral over gradient u times gradient v equals an integral over f times v for all test functions v in h10. Okay, so you probably remember all the steps, If not, please go back to the lecture about weak formulations and try to verify all those individual steps that led us here. And if we talk about the weak formulation for Poisson's problem, then it's always this. Depending on the boundary condition, it might sometimes be U and V in H1 without a zero, but in these standard cases, we're talking about Dirichlet boundary conditions, so H10 as the appropriate space. And that's always important. I've mentioned this many times throughout the last lectures. If you talk about a weak formulation, it's always important to say that U is in a certain space, because that space includes those boundary conditions. Otherwise, it's not a well-defined problem. So the next step was to talk about grids and reference maps. Where we have started was our domain omega. In the simplest cases, just our rectangle here, or maybe even a square. So we've taken that domain. We've defined a set of points, right? In the code we did this with the mesh grid. So just assigned a certain linear spacing in one dimension and in the other dimension, and then created a mesh grid out of those points. From those points, we have connected them to triangles, and important here is that those triangles fill up the whole domain, otherwise we're forgetting something, obviously. So we've connected them. And then what's also important is we've introduced a consistent numbering scheme. Consistent means that this numbering scheme includes certain information. For example, our numbering scheme of the points is follows a certain order. So firstly in the direction of x, then in the direction of y. For the triangle numbering, we say that the one even and an uneven number belong to the same square, so that we might later on use this information. And what's also important is a numbering scheme inside of the cell. So that's not visible here, but if I'm talking about all points that form the vertices of, let's say, T0, then it's important to define a fixed numbering scheme where to start, so that if you talk about T0, you always know that the first point is this one, then the second point is this one, and the third point is this one, or in the usual Python notation 0, 1, 2. And this is then put into an efficient data structure. For this, we have chosen to separate the information into two arrays, one containing floating point numbers with the coordinates of all points. Because we're in 2D, this is a 2-column matrix. And then another one with the indices of points that form cells. And here comes this numbering that I was just talking about. So if you look in row 0 of this cells array, then this corresponds with the cell T0 here. And then there is the fixed numbering 0, 1, 6. And if you talk about the next line, then the numbering is 7, 6, 1, such that we always have the longest edge opposing the first point. So the longest edge of a triangle is always the one opposing the point that occurs first here. And that's, quite an important information. So we see that for both T0 and T1, the longest edge of the triangle is between vertices 1 and 6, or 6 and 1. That's only a reversing of the order, but the same edge. So that we can later on use this information. After doing this, we have defined a reference cell, because we didn't want to deal with the complicated coordinates of all individual cells when talking about basis functions. So we have defined a reference cell, which is a triangle that's super simple between 0 and 1. And for every cell of the grid, we have defined a reference map. So a map that takes our reference cell and maps it in an affine linear way onto the actual cell. And when we defined this, we talked about, so we have like some cell here, A0, A1, and A2, and we want to define Ft mapping from there to there, then we've seen that Ft can be easily computed from the vertices of this triangle. So we can write down a matrix that connects, or using those vertices here. So the first column is A1 minus A0. The second column of this matrix is A2 minus A0 times x hat plus A0. And then if you plug it in, you can all try it out. And if you need more information about this, consult the grid lecture that was given a few weeks ago. Yeah, then we have used our computational grid to define global piecewise polynomial spaces, because those abstract Sobolev spaces, H10 and so on, they are still infinite dimensional. So that's still something you cannot really efficiently handle on the computer. That's why we have replaced them by discrete spaces, and we've chosen piecewise polynomial function spaces, meaning that every function in this space VH here is a polynomial if you are restricting your considerations to just a single triangle. So if I restrict my function V to a certain cell T, then it is polynomial. So it's not a global linear function, but on every cell it is a linear function. And what these functions graphically look like is that they are these patch-wise surface functions. So you take a straight surface on every cell of the grid and you connect them patch-wise. For this space we have introduced a global Lagrangian basis, so a set of functions phi such that they fulfill a Lagrangian condition with respect to the points of our grid, meaning that every one of those basis functions has the value 1 at just a single one point of our grid and value 0 at all other points. They are these hat functions that you see here on the right. Those basis functions are defined also in a piecewise fashion. So for a single point and the corresponding basis function, so if you talk about P15, the corresponding basis function is phi 15 here, then you can identify this to be corresponding to a certain local basis function on every cell. So if I am on T15, I have to identify a certain local basis function. In this case, it's local basis function number 0, because my point P15 was vertex 0 of this triangle, right? It is the one opposing the longest edge, so that has a vertex index 0. That's why it also corresponds with a local linear basis function with index 0. If you need more information about this, that whole concept was called the DOF map. We discussed this, I think, 2 weeks before Christmas. You can consult those lectures again. And then those local basis functions, they are all defined using transformation. So every local basis function with an index I and a local basis function on a certain cell T can be defined using some reference basis function phi I hat and a combination with this reference map. The reason for this concept was that on the reference cell, which has those super simple coordinates, we were easily able to define those basis functions that fulfill a Lagrangian condition, right? This phi hat 0 was something like 1 minus x hat minus y hat, and then phi 1 hat was just x hat, and so on. And in a combination of those simple basis functions and this simple reference map that we just discussed, we were able to define a local Lagrangian basis on every cell of the grid, which is much easier than finding this local Lagrangian basis function using all those weird coordinates of the actual vertices in the grid. And the next step was to do numerical integration, because integrals occur naturally from our weak formulation. We had to get some way of actually handling them on the computer, so that we started deriving schemes for numerical integration in 1D that were able to approximate an integral over an arbitrary function f over some interval from a to b by a summation of certain weighted function evaluations. So you had those weights here that kind of balanced the individual contributions of the points. Then you had those quadrature points, xk. Those were kind of representative points that contain a lot of information. And we have tried to find those rules in a way such that they achieve optimal exactness in the sense of polynomial integration. So we always talked about how high of an order of polynomials can be integrated exactly using a certain number of polynomials. And then there was this upper limit. So if you take nq points, then the most you can get in terms of exactness is 2 times nq minus 1. So for a single point, you get exactness 1. For 2 points, you get exactness 3, and so on. And we wanted to, of course, get those optimal formulas, because that is the most efficient way to go. So it minimizes function evaluations, but gives you the same exactness. And from those concepts in 1D, we went to triangles in 2D, and we introduced formulas to approximate integrals over triangles, which then has an additional degree of freedom, because every point now consists of an x and a y coordinate, so 2 coordinates in a sense. And that gave us different formulas, one for exactness 1, that was just an evaluation in the barycenter. And then for exactness 2, we had those 3 points here. They were all on those lines connecting a vertex with an edge midpoint. And then you can compute the actual coordinates of those points and weights. Furthermore, we have seen that it's not necessary to derive individual quadrature rules on every interval or shape. It's sufficient to do this on some representing reference cell or interval, and then you can, just like with the basis functions, transform everything. So now that we have talked about all those things that were parts of the previous lectures in the semester, we can get to the final point of assembling our linear system. So now let's get to the practical building of the stiffness matrix and the load vector. So for Poisson's equation, we have derived our way from the original strong form, minus Laplacian of u equals f in omega and u equals 0 on the boundary, to this discretized weak problem. So the task is to find dot vector u such that this discrete weak problem, including only the basis functions phi j and phi I, and those dot vector coefficients here, such that this is true for all basis functions. So you can revisit the lecture about the global basis functions if you need more information about how we got there. And this is a fully discrete system. Now, from this, you can define the stiffness matrix with components Sij, just integrating those products of the gradients of the basis functions, gradient phi j times gradient phi I, and this load vector that also includes the external force F. And then this whole task rewrites to finding your dot vector u that fulfills this equation as u equals L. That's exactly the same thing as before, so we haven't changed anything there. The question that we have here is, how can you practically compute S and L? So that's not answered so far. And we start with Poisson's equation. And the load vector is given by the integral over omega of f times phi I. And yeah, the part that follows here has been done already in the lecture about global function spaces, but I'm doing it here because it's pretty important. So we start from this integral over the whole domain, and firstly do a splitting into integrals over the individual triangles. So I say this is equal to a summation over all cells in our triangulation tau h, and an integral over t. Sorry, this hat was not intentional. So it just is, it was supposed to be just the, yeah, you get the picture. Sorry for that. Whatever. Okay. So ignore this part here. So a sum over all cells in the triangulation and an integral just over the cell t. If that triangulation spans the whole domain omega, then this is exactly the same integral, right? So we're summing over those individual triangles, and that gives us the same integral. And yeah, then you can go to f times phi I. Okay, the next step is to replace this global basis function phi I by a local basis function, because now we've said that those global basis functions are defined piecewise using this DOF map and so on. So if I'm now only on a single cell t, I can very well replace this whole thing by sum over t in tau h, sum over t, integral over t, f times, and then there is the local basis function with this other phi letter here, and yeah, the index includes our DOF map, because we had to assign a certain local index to the global index. Sorry about that. Yeah, so the DOF map with global index I and cell index t, and of course we have an additional t up here because it's the local basis function of cell t. And yeah, so now we have localized those basis functions, and the next step is to transform or to include the definition of this basis function. So this basis function was defined using transformation. So we say that this is again equal to sum over all cells in tau h, integral over t, and f times, and now this local basis function on cell t is defined as a transformation of phi hat with the same index d of it, but here with the reference map ft inverse of x. Okay, so now I'm including the arguments here, so this was also of x, right? So this was the definition of ft, phi t, sorry. Okay, after doing this, we can go one step further, and we have seen that everything gets easier if we just transform our integral to the reference cell. So now let's go to again a sum over all cells in tau h, and then we transform this integral over t to an integral over t hat. If we do this, we have to include the determinant of the Jacobian of ft. That was this scaling factor that resembles the area scaling between t and t hat. And then, yeah, it's again f, but now f of ft of x hat, because f is a function defined in our actual domain, so in the actual domain omega and not in the reference. So if you want to put something into f, you have to use the reference map here. And now it's again phi hat with the index from the DOF map. And yeah, but the difference is here now, just like as with the argument for f, we would get of ft inverse of ft of x hat, right? So this ft of x hat is what used to be x, and this is concatenated with the ft inverse that was already there. And then you can here again see that this cancels out because it's ft inverse of ft. So this becomes just x hat. And then we are almost done. And the only thing we need to do now is we need to get rid of those integrals by applying a quadrature rule. So you assume that on your reference cell t hat, you have a certain quadrature rule, w k hat and x k hat, and we do have those formulas, right? You remember, if you want linear exactness, you take this formula with the barycenter. If you want quadratic exactness, you have this formula with the 3 points here. So these are given. And then you can just do this. So that's not an equal here, that's an approximately. I'm keeping my sum over all cells. I'm keeping my determinant, that was the area scaling factor, but I'm removing this integral now and replacing it by a summation from k equal 1 to the number of quadrature points, and I'm evaluating f at ft of xk hat. That here, by the way, was the transformation of the quadrature points. We've talked about this, these numerical integration schemes that can be transformed from some reference to any domain that you want, and that's precisely what's necessary here. So that's f of ft of xk hat. Then you have your phi hat dit, and that is evaluated at xk hat. So we have seen that here ft inverse and ft cancel out. We were just left with an integration of x hat, and that becomes an xk hat. So from the infinite dimensional integral to a finite number of points, and the only thing we're missing here now is times wk hat. And then we are done, because all those things that are written here can be computed now. So let's go from the front to the back. We see here determinant of dft is something we could easily compute. We've done this in the grid class before. So we just took this matrix that occurs in the reference map, that's the Jacobian, and then you form the determinant of this 2 by 2 matrix, so a trivial task. Then in here it's transforming, using the reference map to transform points, quadrature points, and evaluating f. That's also no problem. We know those quadrature points because they are given in our quadrature class. Then you have this basis function here. This basis function can be evaluated at those points. You have the DOF map because that's an assignment of what is the local index of a certain global index in a certain cell. And you have those weights here. You can sum it all up. That's not a problematic operation. Everything here can be done very efficiently because it's essentially just function evaluations, multiplications, and summations. Nothing more. And yeah, let's revisit this for a second. So we started by splitting the integrals into integrals over the individual cells. Then we have replaced the global basis function by the corresponding local one. Then we have included the definition of the local basis here. We have transformed the integrals. This gave us the determinant. And then we have applied the numerical integration. And this was not supposed to be an equal sign. This was supposed to be an approximate sign here. And that's that. So this is now decomposition of this load vector into individual ingredients that we can all compute already. Now for the stiffness matrix the whole procedure is almost exactly the same with just a minor difference. So you start by splitting the integrals and replacing the global basis function by the local ones. So here nothing has changed so far. We have replaced the one integral by a summation over multiple integrals, and we have replaced the global basis function by a corresponding local one using the DOF map. And yeah, then we have included the definition of the local basis function with this transformation approach. Here, when you talk about gradients, it's important to mind the brackets, because you want to form the gradient of the transformed basis function. And that's also the key difference here. That's the only thing that wasn't present before. If you evaluate this gradient of this concatenation of phi hat with ft inverse, then you need to apply the chain rule. That gives you firstly a derivative of the outer function. That's just your gradient of the reference basis function. But it also takes into account the derivative of the inner function ft inverse, and that's the Jacobian of ft inverse transpose. That's something we discussed when we talked about grids and reference maps. It was not problematic to compute this thing, but you have to keep it in mind. The reason for this is that if you if you transform gradients, you have to take into account that if your domain size is changing, a certain the slope of the function has to be adjusted to this change. That's why here, as a difference, you need to apply the chain rule. And then from there, everything goes as before. So you simply transform your integral to the reference again, then you get rid of those ft's. And yeah, so this ft inverse here of x becomes just an x hat, because it's simpler this way. And then you have your area scaling. You keep this inverse of the Jacobian, and then you apply numerical integration again. That is also not changing anything except for the fact that I've again missed this approximate sign here. But this is all just like before, and that's kind of the beauty of those considerations. Except for minor details, everything follows the same order. And again, here it boils down to ingredients that we all have already. We have this determinant that was done in the grid class. We have this wk hat and xk hat that was the quadrature class. We have this dft inverse because that also belonged to the reference map. And we have also implemented the evaluation of gradients of basis functions. And yeah, so we can also put this together. So now, to make it a bit more general, I'm going one step further. The Laplacian operator, which is just Laplacian of u in 2D, is uxx plus uyy. And that can also be rewritten as the divergence of the gradient of u, which is kind of trivial if you think about that. The gradient of u is a vector containing ux and uy here. And then if you form the divergence of this, then this gets an additional x derivative up here and an additional y derivative down here, so that this is also uxx plus uyy. Okay, so that can be done. And then if you include a diffusivity or stiffness constant inside of this divergence, then this can replace, or this can represent, the material properties. We have discussed about this already in the applications of those integrated circuits, where the materials, the individual parts of the wafer, had different electrical permittivity. And that's just one of those diffusion constants here. So that reflects how well your material can diffuse the quantity, or if you talk about membranes, how stiff the membrane is. And that can even be a spatially changing function. That's that example that we saw in the integrated circuits, where you had individually different values depending on where you are in the domain. And this gives you the general diffusion equation. So that's almost the same as before. The only difference is now we have an additional A here. Okay, but the rest hasn't changed so far. We will later on in the results section see how this influences the behavior of the system. The weak form of this is a completely straightforward transfer. So if you multiply with the test function, integrate over the domain, and then apply Gaussian theorem, then this just gives you A as a multiplicative factor here. So it's all the same as before. The stiffness matrix is also the same, and also the assembly process can be treated just in the same way. The only difference is now you also have to evaluate this function A here. And then I can see that I've made a tiny bit of a mistake. So it should not be A of xk hat. It should be A of the transformed xk hat, because A is the coefficient function in our actual domain, so that should be applied to points in omega and not in in the reference. But you see that this can be done in the exact same way, but it gives you the possibility to solve a much bigger class of problems. Then the next step. While we have so far always modeled diffusion processes, so the distribution of a quantity or the bending of a membrane inside of a domain, so always something like equally spreading stuff somewhere, it's also sometimes interesting to consider the creation of the material depending on the already given concentration. So if you, at this point here, if you wanted to add some quantity, you had to put it in externally. So if you think about chemical reactions, so you're in some kind of reactor, then you need to externally put material in there if you want to use F. But sometimes this is not the case. Sometimes it's going the other way, that the quantity U creates itself using chemical reactions. That gives you a term that represents the creation of the quantity depending on the level of U that is already present. So if you look at this term here, then you see that this is essentially different from the F that we had before, because this one scales with U. So if you have a zero concentration U, then this term simply does nothing. And yeah, this is controlling how much is produced depending on the quantity that is already there. Important, interesting question. We have talked about the pure diffusion problem, so the Poisson equation, or the more general pure diffusion problem, but we haven't discussed the pure reaction equation, only this reaction-diffusion combination. And why is that? Well, if you think about the problem, C times U equals F, so that would be kind of the pure diffusion, the pure reaction problem, and add those boundary conditions, U equals 0 on the boundary, then you can easily compute the solution of this problem by simply dividing by C. Then U is given by F over C, and that has exactly no degrees of freedom that can be used to adjust to the boundary conditions. So U is just written down like this, and if this fulfills the boundary condition, you're lucky, but if it doesn't fulfill the boundary condition, there's just nothing you can do. And that's why it doesn't really make sense to consider pure reaction equations, because they are not differential equations in a sense, because it's not there is no derivative involved here, and then it also gives problems with the boundary conditions. The weak form of this reaction diffusion problem is also simply to be computed, so you can again multiply that thing with a test function V, and integrate over the domain. You don't have to do partial integration here because there is no derivative involved anyways. So if you look at this problem again, then it is just c times u. So if you think about multiplying with v and integrating over omega, you arrive here immediately. That means the stiffness matrix is now a combination of two sums. So you firstly have your diffusion problem that you had before, and you also have this new term here in the stiffness matrix. And that's something very common for more advanced FEM problems. Your stiffness matrix always follows the same structure, but it is usually computed as a summation of individual contributions from all of your operators. So some second order terms, some first order terms, some zero order terms, and so on. And that assembly is also a direct transfer. So the first part that comes from here, that just stays the same as before. So I haven't noted this again. But then if you follow those steps that we have discussed before, then it again works in the exact same way. So you can just do your localization, you do the transformation of the integral, and you apply your quadrature rule. Again, this here is wrong, just like before. So this should again be c of ft of x hat, because c is again a coefficient function in your actual domain. But as for the rest, you see here again, this follows the same schematic as before. And then, one step further. So far we have diffusion, so we have spreading of membrane material or quantity U or something inside of the domain. We have created U by chemical reactions using this reactive term, and we have applied external influences using F. But what we haven't done is transport. And if you think about, for example, a chemical reaction in some reactor, then you would probably have some type of swirling or something else to mix the whole thing up. So you would always have some transport influencing the whole stuff. And that's what can be included using this first order term. So while the diffusion term had two derivatives, so divergence of gradient, right? And the reactive term had no derivative, so just c times u, and this external influence F didn't even contain u. So that would be like, this is u2 prime, this is u0 primes, and that is without the u at all. So what's missing here is one derivative of u, and that's a scalar product of some vector field B and the gradient of u. And that precisely models transport in the direction that is represented by B. So if your vector field B in your domain, for example, it might be a constant vector field pushing just in a certain direction, or you might have some swirling, let's say, so that B is going in a circle like this. That all can be modeled using this convective term. And then the direction of magnitude and the magnitude of B control the transport, and it can be imagined as an underlying flow. However, this is not capable of modeling complex flows, for example, with turbulence, like Navier-Stokes can. This is just very basic flow. So it can be, if you want to imagine this, you should maybe imagine like a very steady stream in a certain direction, or maybe wind pushing your quantity. And here again the question, we have a pure diffusion equation, but we don't have a pure convection equation. The argument before was that this pure reactive thing would not be a differential equation at all. So what's the problem now? Think about a one-dimensional example. So you have an interval AB, and then this pure convection equation. So in 1D you don't need a scalar product, right? It's just b times u prime. So u prime is just the gradient in 1D. And you have your Dirichlet boundary conditions. Then, well, what would you do? Well, you would reformulate that whole thing and say u prime of x is f of x over b of x. And then you would formally integrate that whole thing. So you're saying that u of x, your primitive of the whole thing, is the integral over f of x, so the primitive of b over x, plus some constant, let's call it gamma, for example, right? That's what you do when you form the primitive of a function. And that gamma here is a single number. That gamma can be chosen to actually fulfill your boundary condition. But gamma is just one number, so it can be chosen to fulfill a single one boundary condition, but not at both ends. That's why your standard ordinary differential equation in 1D or also in 2D only has initial conditions and not boundary conditions. Because if you have one derivative, you arrive, so this one derivative here translates into 1 degree of freedom. And that 1 degree of freedom can be used to fulfill a single boundary, but not boundaries on both sides. On the other hand, if you have something like u double prime equals f, then you would have u prime is the integral over f plus gamma, and then u would be the integral of f plus gamma plus some, I don't know, delta. Right? So if you, with every derivative, you get an additional degree of freedom, and that's important here. So also a convection equation cannot fulfill boundary conditions everywhere. And that's an important observation. We need this in a few minutes. So that just doesn't work. So we always need this diffusion term here. And then we can add first order or zero order terms as we like. So now here the weak form is also pretty trivial. So you just take your equation b times gradient of u that you can see here, and then you multiply this with a test function v that is just a straightforward transfer. You don't need partial integration, however you could do it. So there is also ways to partially integrate this. That's not necessary here, but could be done. And yeah, then you insert your basis functions and so on. And then here it's for the first time an asymmetric operator, I would say, because one basis function has a derivative and the other one doesn't have a derivative. The one without the derivative can be evaluated in the straightforward way. The one with the derivative needs, just like before in the diffusion term, this chain rule here. And now here, for the first time, you see why I was emphasizing so many times that Sij is given by a product of phi j times phi I. In the original Poisson equation with just the Laplacian to discretize, it didn't make any difference because there the whole thing was symmetric anyway. So if you would change those, that's not a problem because that's symmetrical. Here, it's not symmetrical. So here it makes a difference. You cannot just change ansatz function and test function here. So please always be careful with this indexing. But for the rest, I would say if you know how to assemble your diffusion term and you know how to assemble your load vector, then it's super simple to combine those two to also assemble this convection term. So the most general problem we're discussing here is this general reaction, convection, diffusion thing. So you have your convection, you have your, this was a diffusion, you have your convection, you have your reaction, and your external force F. The weak form of all of this can be computed just like I've said before. A, B, C, and F should be L2 functions. That's the minimum requirement for this, for this to be well defined. And B should also be an L2 function, but it should be vector valued because it kind of reflects the flow field that's underlying. And then your stiffness matrix can be simply computed by combining those considerations that you've seen from the individual contributions. What's open, and you might have guessed this already at this point, is the discussion of the boundary conditions. And we have completely ignored them so far. So we have said that we were looking for functions u in the weak form that were in the space h10. And then we have simply replaced h10 by this space vh of piecewise polynomials. And then we have talked about assembly of this linear system, but there was never a talk of boundary conditions ever again. And we need to correct this problem because otherwise we simply won't get boundary conditions to be zero. I mean, if you set up the system just like we did in those last few minutes, then why would the solution be zero in the boundaries? We have not done anything to achieve this. But it's not so simple. So if you think about your domain and those points that were used to construct your grid, then the first step to include boundary conditions is to identify the indices of those boundary points. So in this simple structured grid, it's quite easy to identify them. And then if you have them, you introduce boundary equations into your stiffness matrix and your load vector. That is something you have heard already when we talked about the finite difference method. And I can tell you at this point it's exactly the same way. So you want to include equations into your linear system that enforce the boundary conditions to be true. How do you do this? Well, you insert equations in the stiffness matrix that if my point I, so if my row index is a boundary point, because this 0 is listed here and this 1 is also listed here, so those are both boundary points, then you don't assemble the matrix by using these considerations as before, because at point 0 and point 1 we don't want to compute the solution from the PDE. We just want to put the boundary condition there. So you simply put a 1 on the diagonal, and if you put a 1 on the diagonal, then this individual line, if you multiply SUJ times U, so you take your dot vector and multiply it with this row, then this gives you just UI. So that's just the point, the value of this dot vector at this individual point. You can verify this easily because it's just 1 on the diagonal and 0 everywhere else. And yeah, if you have done this, you take the load vector, and in this individual row of the load vector, you put in the boundary condition. So if you have a problem like this, this was the more general case with a non-zero boundary condition, but if you have 0 boundary conditions, you can just do it exactly the same way. So on the left-hand side in your stiffness matrix, you put 1 on the diagonal to get this equation UI equals something, and that something is just the boundary condition. So you're just including an equation that enforces your boundary condition. And even though this this equation has a trivial solution, this individual one, it's important to include it because, well, if you think about the dynamics at this point here, then they are of course influenced by the values here. So we just need to include this boundary equation such that we can also get the other points properly. So this is exactly the same way that we did in the FDM. So if you want to look at an example how those matrices are looking in those individual rows, go back to the FDM lecture. There it's done. And that settles our open question of the boundary conditions. So we can now say that this stiffness matrix is assembled by two types of equations. First ones are boundary equations, and the others are the actual problems equations from the PDE. Finally, after investing that much work, let's get to some results. We start with Poisson's equation, so the simplest you can do. We talk about the domain 0, 1 square, so just the unit square, equation minus Laplacian of u equals f, and we take Dirichlet boundary condition, so u equals 0 on the boundary. And that gives you this. So having implemented this assembly process that we have just talked about, it's, you get this as a result. So you compute your stiffness matrix, you compute your load vector, you solve this whole system, and then you plot this Dov vector. Then this gives you this. This is not very spectacular, but it reflects the kind of behavior that you would get if you take a membrane and push from below onto the membrane. But what's more interesting probably is what happens if we change certain things about this equation. So if you replace this, if you include a smaller diffusion constant here, so this 0.1, then in order to make it visible, I am going back one slide. You had 0.07 here, and now you get 0.7. Okay, so if you reduce the stiffness by including a smaller stiffness constant here, you increase the total elongation of this membrane. Okay, so that kind of makes sense. So if you replace, you take your stiffness constant 1 and go to 0.1, then your membrane is 10 times less stiff than before. That means your maximal elongation goes from 0.07 to 0.7. Okay, that's also not super shocking right now. Now, so that gives you an idea of what diffusion practically means. Now it becomes more interesting. Let's include a reaction. So instead of just considering our Laplacian here, I'm adding plus u. So reaction with a constant 1 as a reactive factor. What would you expect? Well, you would probably expect that you now have more of the quantity u in there. What's actually the case is that it's getting less. So in comparison to 0.07 that we had for this problem, there we had 0.07, we now have 0.06, so it's gotten fewer. And that also kind of makes sense, because if you think about ignoring this reactive term here, then this equation, the solution of this equation, already gets value 0.07. But now if you add a positive reaction constant, meaning that you put in the creation of some quantity u with a positive factor, then this means that you need less u to get the same total balance of f. Okay, so if you want to add positive reaction, you need to take a negative sign for u. So that's something you need to be aware of. Now, yeah, if you increase the value of the reaction even more, then you get an even smaller result. So if you would let this here go towards infinity, then you would approach a constant zero solution, because this means that you have infinitely much creation of u. So no matter how much u is there, you're creating infinitely much, and this all equals just your originally constant that I should have mentioned before. So f was always just 1, so the constant 1 function. And so yeah, if you create infinitely much and it adds, depending on u, and it adds up to just 1, then there needs to be a super small amount of u present. And yeah, but you never get an actually negative sign. Okay, now here comes something a bit more tweaky. So I've added a function here for the reaction that is not constant inside of the domain, but instead it is changing. So if you think about this, then this is just the constant, the value 0 here in the bottom left corner of our domain, and it's very quickly increasing. So it's like almost doing nothing here, and then it's quickly increasing here at the end in both directions. And yeah, what this is doing is it essentially leaves the membrane behavior unchanged, more or less unchanged here, close to the point 0, 0, because nothing is happening. And over here, when this reactive term becomes larger and approach this actual value of 500 here, then you see that this pushes the solution down, because that's the argument I was talking about before. So you again have your constant right hand side here, and then if it adds up to this, then there must be very little of u present somewhere. Okay, and the last part we want to talk about is convection. So instead of doing a reaction, creation of more quantity, we take our u and push it in a certain direction. And the direction is prescribed from this vector, and this vector is pointing diagonally into the corner of 1, 1. So if you think about your domain, then it's doing like this. And I've chosen it to be 10 and 10 in order to make it visible enough. This takes your stack and pushes it into the corner. Now what's important here is that in contrast to this weirdly shaped reactive thing that actually changes the amount of material, we now have taken the same amount of material, so the integral of u is unchanged when adding this convection term, but we're only pushing the same stack into the corner, okay? It only shifts the material into a certain direction. Okay, let's do a quick summary of those individual parts. We have reactive terms, we have diffusive terms that just model spreading of a quantity or a membrane, and they are there to make your problem solvable, because we need a second order problem that we have seen before, and it just balances it all out. You have your convection, that's a directed transport of the quantity in the direction prescribed by B. You have creation of the quantity depending on the amount that is already there. And you have external forces. So F just puts in stuff from the outside of your reactor. So if you think about a chemical reaction, then this first part here makes sure everything is well balanced. This is the swirl that's mixing everything up actively. This is the creation, so the chemical reaction that's happening, and this is putting stuff in from the outside. Outlook, singularly perturbed problems. So yeah, we take this setup and create a problematic one out of it. Why? Because the reason why I'm doing this is because I want to motivate that not everything is great right now. So we have created a very powerful setup to solve our different types of partial differential equations with boundary conditions, but we are still not able to solve all types of problems, or some of them need special attention. And one class that needs a special attention are the singularly perturbed problems. Why are they called like this? Well, if you look at this, then you have a small factor in front of your Laplacian and a somewhat large factor in your convection term. And that reflects exactly what we have discussed before when we argued why it is not possible to create a pure convection equation. So if you think about this, then this is strongly dominated by the convection because that's bigger. And if you would take a limit and make this even smaller here, this 0.1 factor, then you would go in a limit to a first order equation. So in the limit, this second order term wouldn't even exist. So in your limit, you could not fulfill this boundary condition because the first order one cannot fulfill boundary conditions at all boundary points. That's what we have seen before. That means if I have an imbalance between the second order derivative and the first order one, and the imbalance only in one direction, so you have a strong convection and a weak diffusion. That same problem also happens with, or a similar problem happens if you have a strong reaction and a weak diffusion. So the key is here that the diffusive part that is necessary to fulfill your boundary conditions is too weak in the whole balance. If that happens, the solution looks terrible. So it still kind of has the same idea, I would say, as before. So it's still kind of shifted into the upper right corner, but not really. So it's still, it has these spikes, so it's numerically very unstable, and it doesn't really look good. So it doesn't really work anymore. And if you reduce your 0.1 to a 0.01, this gets even more terrible, and now in this case you are not even preserving the original behavior anymore. So if this one goes in the limit to 0, you are approaching a problem that is not solvable. Okay, that's fine, we don't want to solve it, but because we are always interested in second order problems, but there can be practical examples where it is small, the factor is actually small. And one common example is from fluid flows. So if you have a Stokes problem that has so you have a turbulent flow, then you get a very small factor epsilon here, that's 1 over Reynolds number. We will be talking about this in the next lecture. So you have a small factor here in front of your Laplacian, plus some large convection. This is common in fluid flow problems. There you get problems at the boundary condition, at the boundary points. And so far, we cannot handle them. But next lecture will be all about discussing what to do in order to address those singularly perturbed problems, and more generally, what to do to get our numerical setup perfectly suited for the problem we are dealing with. So now we have to, after being happy that we can solve our system, we have to address certain individual problems with them. So the next lecture will be about what to do if it doesn't work like this.